Mario, how do you connected?
Are we expecting anyone else?
I got something for Robert here.
Okay. All right. I think we're 10 minutes past the hour, so we should probably just start. It's my pleasure to introduce Sebastien Foucaud, who has been visiting us this week from Shanghai, China. You might notice that Sebastien may not seem like a typical Chinese astronomer. That's because he's originally from France. And you correct me if I'm wrong, he did his PhD in France, then did postdocs in Italy and the UK, working on UKIRT UDS, among other things, and CBCLS for doing his PhD thesis. Then moved to China, where to Taiwan first, where he worked on Pan-STARRS, another big survey that has lots of obvious connections and comparisons with LSST, and finally moved to Shanghai a couple of years ago, and I guess in Taiwan started working on the HyperSuprimeCam survey, HSC, which is actually one of the surveys that's using LSST data management code as their base for their data management stack. So Sebastien has had lots of experience with big surveys, and his science interests are driven by that. So he's going to talk to us about the evolution of dark matter and baryonic mass assembly through cosmic time, a problem that has a lot to do with deep imaging and understanding what's going on when you stack lots and lots of images. So without further ado, I'll stop and hand it over to Sebastien. Thanks.
Okay, thank you very much. Thank you for coming, and thank you for having me here today. I know that I'm testing for the first time this system with Hangout, so I hope everything is going to run smoothly. Please feel free also to interrupt me anytime if you have questions. I've been teaching quite a lot to a huge assembly. Last semester I was teaching to 200 students at once, so I'm used to be interrupted. No problem with that. And yeah, so I'm living in the Chinese world for 5 years, so I have a Chinese name. It's here, it's called Foucaud, which happens to sound exactly like my name in French, Foucaud. That's why they choose that, which is pretty fun. And the meaning of this character is master, so teacher. So that's pretty well fitted with my function in China. And this means valley and stone. So I'm currently in Shanghai Jiaotong University since a year, but I've been involved in many different surveys. Some of the results I'm presenting here today are related to the UKIRTs. I'm still working on the UKIRTs dataset. And at the end of this talk, I will briefly introduce why I'm so interested in the next generation of survey, HSC and LSST in particular, and which are the problems that can't be addressed with the current generation of surveys that we need to address in the future. And I'm working on galaxy evolution in general, in particular their relationship with the dark matter. So this is a brief outline. I will introduce you to the topic, galaxies and dark matter halos, and then show you how we can probe actually the relationship between galaxy and those dark matter halos at even very high redshift or very distant galaxies using techniques, statistical techniques called clustering, and running some sort of model of the distribution of halos in the universe to probe the mass of dark matter that is related to the galaxies we're looking at. And I present you a focus on two very recent results I've been working on with my team in Taiwan. So two papers, one is about to be submitted, and the other one is online actually on AstroPH since Monday. It's accepted on APJ. One related to how we can probe the total baryon mass in galaxies. That means stars, but also gas, and we developed a technique for that. And the other one related to merger rate of galaxies and how we can probe the evolution of this merger rate, which is a very important phase of the evolution of galaxies. And then I very briefly, if I have enough time, go through why we want to do HSC and LSST to address some of the issues I raised during the talk. And I'm not sure I will have time, but show you also that I have been deeply involved in data mining and operating huge data sets and trying to get sense out of it using unsupervised machine learning tools. So I go extremely briefly on that, focusing mainly on the science. So to set up the background, is we are now in cosmology and galaxy evolution have a very well-established framework that we call the lambda CDM model. It's a paradigm mainly driven by cosmology, and the state of the art after the most recent experiment, like Planck, for instance, is telling us that if you look at the budget of energy in the universe, there are two big surprises, and actually the two biggest questions to address for the whole physical community for the next decade, which are dark energy. So dark energy is only probed through the fact that we realized 20 years ago that the universe is expanding faster than what we were thinking with a standard model. And the only way to explain this expansion is to somehow add an extra amount of energy for the galaxies to move away one from the other faster than it is. So this dark energy can take many, many different forms. It's a very hard problem that is ongoing studies, and lots of the surveys that are developed currently and will be developed in the future, like HSC, DES, that are running now, try to address this issue. The second big question mark and a big surprise that we discovered in the past 50 years is this existence of dark matter that not only exists but also seems to dominate the budget of matter in the universe. And the only way to really probe the evolution of dark matter today is by gravitational interaction. We just probe the existence of dark matter by the fact that gravity is behaving like there is more mass than what we observe when we're looking at stars and gas. So we have a total budget of 95% of what we don't know, and a budget of 5% that we know. And we can probe all the rest only through this. And mainly, in the past several centuries, we have been focusing only on very few things, stars. And even today, the day of today, it's very difficult to probe free hydrogen, just because it's possible to observe it directly. So even today, everything that we know is probed by observing 0.5% of the universe. So why we are sure, well, just quite secure nowadays with this framework, is because it has been extremely successful in explaining things that happen on large scales. So if you observe the universe as it was when redshift were around 1,000, as probed by the cosmic microwave background, we see that the universe was extremely smooth, which is actually a very big open question. I won't point at that today. But the universe is very smooth, and actually the contrast between the highest peaks of temperature in the cosmic microwave background and the last one is the order of 10 to the minus 5. But when we look at the state of art of a large-scale surveys at redshift 0, like for instance the 2DF, but also DSS is another example, we see that the universe is actually extremely structured. Each blue point here is a galaxy. We see that galaxies are actually located in filaments, walls, clusters, and there are voids. And the contrast, more or less, if you take from the peak of the filaments to the bottom of the wall of the void, is 10 to the 5. So we have an evolution of contrasts of 10 magnitudes throughout the evolution of the universe. And through this paradigm, we managed to explain it extremely well. So actually, it's as simple and surprisingly that we don't know what dark matter is, but we can prove very well its behavior and model it very well. This is just a small diagram that I extracted from my PhD thesis. The idea is that dark matter is distributed, and there are some primordial fluctuation. And when a fluctuation at a given time is going above a certain threshold, and collapse and form a dark matter halo. That's how we call it. It's probably a clump of dark matter more than halo, but it's easier. Halo involves always this idea that things are spheroidal, but we know that there is no spheroidal chaos. So then the lambda CDM naturally explains the formation of the structure we see today, as I showed you in the 2DF, by merging. So those halos merge together, bigger different halos at different locations, and they merge together to form the bigger structure today. It's a hierarchical formation. And this is represented here by what we call a hierarchical tree, which is, I'll show you one other later. So the time is going from top to bottom here. This is from a paper from AstroInformatics. And here it just represents some small structure that merge together with time to form the bigger one. The bottom line is, in that context, we have models and simulations that explain very well the formation of the large-scale structure. The problem is, typically galaxies are not very good tracers on underlying matter, because this little 5% of is subject to a lot of physics, and the physics of star formation and the relationship between gas and stars is extremely complex and nonlinear. So we're still failing to really reproduce it in computers. But surprisingly, dark matter, because we assume that it's not interacting, so it's just interacting through gravity, is very well constrained. The behavior evolution of dark matter halos is very well constrained. So yeah, what I said is the difficulties today is the interplay between star gas and dark matter halos. There are lots of physics happening, merging of galaxies, I've mentioned today, cooling of gas, star formation, the role played by black holes, the role of feedbacks of black holes in star formation. And for the past more than 10 years now, my scientific interests have been driven by this problem. It's trying to relate this physics to the dark matter halos. And why do we want to do that is because today we're probing all those large scales by following galaxies, and we still don't understand exactly what is the direct link between dark matter halos and galaxies. So we want to assess that, because in the future we're going to gain a very, very high level of precision of the distribution of those galaxies, and the physics behind will be a problem. It will be a systematics to constrain things like dark energy, for instance. So you really want to dip into that and really understand very well how stars are formed and how galaxies interact with their dark matter halos. So we have a framework of the lambda CDM, and we now have very, very good models. So this is an example of n-body simulations. Here, everything that is showing is actually dark matter. So you start with a very smooth distribution, and with time, due to the effect of the expansion of the universe and the gravity, you form very, very highly dense structure like clusters and voids. And this is not only qualitatively, but quantitatively reproduced very well. It's very successful in reproducing what we observe. So how we plug into that the galaxies, so the best way we are doing currently is called semi-analytical models. We use that as a framework in which we plug artificially recipes for evolution of galaxies. So we assume that galaxies will form where dark matter is, because gravity will be dragged into this potential. So galaxies would form there. You will have gas collapsing, and the gas will the density will raise, and you will have all the cooling phase and the formation of stars that will happen. And then merging between halos will happen, merging between galaxies will happen too. And we can, using many, many different recipes, try to reproduce how galaxies should look today. In fact, we're doing the other way around. We use how it looks today and use it as a starting point to show how galaxies were in the past, and we can compare with the real universe. And also, the physics inside dark matter halo or galaxy doesn't know which epoch it is of the evolution of the universe. So the physics has to be the same, but high redshift universe is a very different place. The contrast density is lower, so somehow the physics here should be more easy to detect. So that's one point why very early in my career I put a lot of phases in high redshift galaxies. The physics, the link between galaxies and dark matter halos should be easier to understand there, because they don't have those very long process of evolution of the galaxy populations in between. So we have those wonderful simulations models, but what we observe is only galaxies, and once again have to put a lot of phases. We're just proving here 0.5% of the whole energy budget in the universe, and we have to relate it to the whole evolution of the galaxies and dark matter and dark energy. So we're using, so this is a CFHT. I am French, so I showed a picture of CFHT. I did actually lots of run of observations when I was a PhD student there, and I've used at early stages the CFHT LS to do my research. So how do we do that in practice? How do we collect galaxy and halos? Well, we assume that there's a different distribution of halos that, once again, is pretty well constrained by the lambda CDM model. And then we plug it inside galaxies with different colors. And then, because we observe only that, the difficult step is how we jump from here to here. So how do we physically incorporate galaxies inside models? And this is what basically we're calling halo models. And we have several sets of observations that help us constraining these models, how we plug galaxies into dark matter halos. So the halo occupation distribution models, as they're called. So now, if you do that, what you can do is probe something as simple as the evolution of the ratio of stellar mass to dark matter halo as a function of the mass of the dark matter halos. That's a game that has been played at redshift 0 for many, many years now, and we have essentially, and it looks like that. So we have a peak where at around 10 to the 12, which corresponds more or less of the mass of the dark matter halo of the Milky Way. We have a peak of efficiency for star formation. That means you have, for a given amount of dark matter halo, you have plenty of stars. And when you go to low mass, it's dropping, and high mass is dropping. Here we are probing clusters. And we know that the main part of the baryons, for instance, are stuck into very hot gas, for instance. So to probe this, to probe the dark matter halo in practice, we have a toolbox that we can use at redshift 0. So first are those statistical studies that I will describe a bit more in a minute: conditional density function, abundance matching, clustering, and those models, HOD occupation models, have been used extensively at redshift 0. Then we can use weak lensing. We know that the presence of this clump of dark matter has a role to play with the deformation of the shapes of the background object due to gravity. So we can probe back using background galaxies the amount of mass we have in the halo for foreground objects. We can also use directly dynamics, like in cluster, measuring the dynamics of galaxies within the cluster to probe what is the total mass within the cluster. Oops, wrong button. Do that. Okay. And the last one has to do with a cluster, directly study of clusters and group contents. We have several direct observations through, for instance, the hot gas. That is a good proxy for estimating the total amount of mass in the cluster. This works very well at redshift 0, but when you want to go to high redshift, detecting clusters is very difficult because the contrast is very small at high redshift. So we can't really do that. We lack background galaxies when we want to push at redshift 3 or 4, so we can't do that. So we have just to rely on the statistical techniques. So to describe briefly what is a clustering analysis, well, it's exactly like this. This is from a picture taken in Seattle. It is called Mango Dancing in the Street. And the idea is that we know what are the steps, but we don't know what is the music. And that's more or less what we're doing here. Is we are probing the distribution of galaxies statistically and relate that somehow to the distribution of dark matter halos. So clustering analysis is just measuring the excess of pairs over a random distribution at different scales. So for instance, for a given scale, here you have a very high clustering, things are very clumsy, and at the same scale, here things are more randomly distributed, so the clustering would be larger. And we know that basically clustering is following a power law. And this clustering strength is evolving with the scale. So R here would be the physical scales that are measured here, and we prove it for different R. So typically what we're using in this world, we have this R naught that is called the correlation length, that is basically telling you the amplitude of the clustering strength. And the higher R naught is, the more cluster your galaxy or your sample is. So here R naught is very large, and here R naught is very small. And so we can do that. I've been doing that since the 2000s, measuring for different samples. You select a given sample, you measure the excess of pairs over random at different scales, you get a power law, you measure the amplitude, and you can interpret basically which kind of environment galaxies are living in. We even push this measurement to very high redshift in this paper from the survey. All these are from the UKIRT with Ross McClure. And the next step, the natural step, is to compare with what those predictions from lambda CDM models are giving us. So it's extracted from a paper from 2010. This is the correlation length R naught versus the redshift. So these are my measurements here. And the colored line here represents what this measurement will be for halos of different masses. So from 10 to the 10 times the solar masses to 10 to the 13. What you can do as well is you can split your sample in different stellar masses bins or in different colors and just compare basically what kind of environment, what kind of mass of halos your galaxy is living. So this is a very simple way of halo modeling, and if you go to the next step, then you can basically, for each of these points, assign a mass of halo and go back to the stellar mass to halo mass distribution that I showed previously. And here, it's a very simple halo distribution model. I assume that I only have one galaxy per dark matter halo, which is wrong, but for the very massive galaxies, probably not too bad as an assumption. And as you can see, the measurements I've done that were done for the first time at redshift above 1, no one have done that before, we see that we're following at high mass the trend that the underlying points are showing you what's happening at low redshift. And you can see the trend also evolving with the redshift. Here, we see a drop of this ratio with higher redshift, and still an opposite question here. Just to give you an idea, this line here corresponds to the average value in the local universe, and this is the average value of total baryonic fraction coming from the CDM, coming from the CMB. So that means that here we have stars plus gas, where all my points are only stars. So we have this trend, and the question is, why are we missing baryons here? So you can compare that with semi-analytical models. That's what I have done. I compare with the millennium, so the same trend, and you see that actually the models reproduce very well the shape I've been showing you for several slides, even at higher redshift. But the reason is pretty well understood, in fact. So what happened when you go to the low mass? And first, what happened is that if you have a very small dark matter halo, you won't have enough gravity to pull down all the gas together and start forming stars. So here, dynamic scales are too long, so you can't form new stars. On the other hand, if you go to very massive dark matter halos, what happens is the dynamics is not a problem, but then you have lots of gas heating up. So cooling time scale is very, very long. So you're very inefficient for new stars. You can add up to that, so and you will have lots of hot gas. You can add up to that, especially at the low mass, the effect of feedback of supernovae. I mean, as soon as you form a supernova, it will just expose completely the gas out of your halo. So, well, it's pretty successful. And if you start thinking about what am I missing in terms of galaxies and adding the satellites, so here, once again, I was assuming only one galaxy per halo, but in one given halo, you may have several other galaxies. So we have statistical way so work from Xiaohui Yan and Simon Weiman for this DSS to probe satellite within groups. And you see that if you add up the amount of mass that is stuck in satellite, you're coming very close to the local value, the rest being represented by hot gas. But semi-analytical models completely fail to probe this evolution with redshift I've demonstrated with my dataset. So is it a problem with the dataset, bias, or is it coming from the semi-analytical models? Well, I didn't have the answer in 2010, but now there are several people like Reddy and Steidl that had the idea of using some recipes to see how this ratio will evolve for a galaxy as they see them at redshift 2.3 in the past. So they're using different models to explain that, and they probe basically a similar trend for star galaxy. So that's quite interesting. So there's something going on here. So definitely we want to explore this kind of behavior at high redshift to see what happens. I told you that we need to go a step further. We need to basically to probe how many galaxies we have per dark matter halo. This is the real halo aggregation models, and this is the way we're doing it. When you look, there has been a surprise 20 years ago, is when you look at the clustering analysis at very small scales, we see that it's diverging actually from the normal polar. If you probe at large scales the clustering analysis, you see that it's actually the polar is steeper when you go towards the small scales. And the way we explain it is that at large scales, we're dominated by the distribution of dark matter halos, but at small scales, we're dominated by the distribution of galaxies within dark matter halos. So by just using the clustering analyzing tool, we can plug in a model of distribution of a number of satellites we get as a function of the mass of the halo, and then probe how many galaxies we have per halos. And it has been done very successfully applied for many samples. This is a work on the CFHTLS by Jean Coupon, who used to be a postdoc in Taiwan, and still working with another project I'll present in a minute. I'll jump on that. So now we have all the toolbox necessary to go and re-understand the relationship between highly stellar masses and dark matter halo masses, even at high redshift. And there are several direct conclusions out of this work. The first one is here. It's, for instance, a result from Alexi Lauto, where she combined clustering analysis with reclancing. So So you get a very accurate measurement of this evolution. You see that once again, we still have the same shape, peaking at around 10 to the 12. But the question is now, what are we missing? When you do this assessment, you're still far away from the average baryonic fraction. So where are all the baryons? And the question is, we know that probably if you add the fraction of baryons in hot gas in clusters, you probably can pop it up to the value from the CMB level. But we know that we're still missing some of them. And on the other hand, if you look at what happened in very low mass halos, this is velocity, it's the work from Macro et al. So this is the mass of baryons as a function of the velocity of galaxies in a given halo. You see that you diverge from what you would expect from the local value. So here, once again, we are missing baryons. And the response here is that the baryons are probably in outflow, so they're outside of our halos. So to have a very, very good assessment of the evolution of the relationship between galaxies and dark matter halos, we need to go one step further. We need to probe the whole amount of baryons storing gas and stars together. And this is, for instance, a very nice plot. So it's coming from semi-analytical models. So it's a model, it's not reality. From Rachel Somerville, showing the mass, the ratio of mass baryonic and halo as a function of the mass of the halo for different type of baryonic matter. And so the black boxes here are for the whole baryons. Well, the scales are weird, that doesn't matter, it's not the point of this diagram. So you see, when you probe at high masses, you're dominated largely by the hot gas. And when you go to intermediate masses here, you're somehow dominated by orange, which are stars. But very rapidly, at low mass, completely dominated by the cold gas. So if you really want to assess the amount of baryons in galaxies compared to dark matter halos, especially at low dark matter halo masses, you need to probe the cold gas somehow. So this has been done in the local universe. You can use H1 surveys, that's H-alpha, for instance. So here, this is a work from Papastergis in 2012, where he shows here the baryonic mass function at redshift 0 for total baryon in black, in red coming from the stellar mass measurements, and in blue coming from the H1. Here it's coming from radio measurements, but we can do at low redshift, but we can't do at high redshift. And here is showing the effect that it has when you probe the ratio of baryonic mass to halo mass versus the mass of the halo. So at high mass, we are dominated by the presence of stars, but when you go to the low mass, then you definitely need to account that all the baryons that are stored into a cold gas that are not formed into stars yet. So that's the starting point of the work. I started something like a year ago with several collaborators, including Jean Coupon, and I'm using probably the best data set so far to do that kind of jobs, which is the UKIRT Infrared Deep Sky Surveys Ultra Deep Survey, or UKIRT's UDS. So this is a survey that is very close to my heart because I've been the survey scientist for 5 years when I was in the UK. So I was responsible of making the data publicly available from the start of the observations to the release in the database. And we had a very successful history. There are more than 60 papers that were related directly to the use of the UDS. This is the UKIRT here. We are now, the survey is over, and we are now at release, I think we are now at release 12, but it's not been even released towards ISO. The way UKIRT is operating is that it has a data release once a year or twice a year, depending, to the ISO community. And 1 year after, this data is public to the world. So currently, I think at the day of today, if you are interested, you can use DR8. So it's a near-infrared survey. You can get K, H, and J, this kind of depth AB. And the one I'm using here is public, is only public to, only available for the ISO people. And I kept my data access right when I moved away from Europe. And you see that we're going down to KB 25.1, 25.2, which makes it de facto the deepest near-infrared survey ever conducted from the ground. And the idea is that we're probing a large, good volume here because the surface, the area on the sky is 0.8 square degree. If you want more information, there are a couple of papers that describe the survey here, including mine in 2007. The other advantage of this field is we have a large extent of auxiliary data sets available, from optical to far infrared to radio millimeter. And also very deep spectroscopy from VLT and VMOS and FORCE2 that focus on high-redshift galaxies, for to be very important for us. And one component that is very important as well is the U-band. I'll come back on that. A very deep CFHT U-band. So this is just a summary of the depth reach. This is the footprint of the sky. So unfortunately, our Japanese friends have been excessive in exposures when they were taking this data 15 years ago. So we have lots of halos around bright stars, but still we're covering 0.6 square degrees here. And all this data set is very, very deep. You see that we are, the U-band data is 27.2. It's 26 or 28 hours of CFHT data. It's the deepest U-band stack ever made for CFHT so far as well. So we have both very deep U, very deep U, very deep optical, very deep infrared. So we can do a lot of nice work. And in extraordinary astronomy nowadays, everything relies on this kind of dirty job, which is measuring photometric redshift or stellar masses. And the way we're doing it today is basically taking a set of templates, introducing a galaxy population, run this into the filters that we have, and it provides us basically colors, and you compare the colors of our object to these templates convolved to the response filters. That's what it gets when you do it. So this is a spectral energy distribution of two galaxies that redshift around 1 and 1.3. And the green line is the best fitted template. And here you have the probability distribution function of the redshift. And each black points correspond to the photometry we get in those different bands. So what you can do after is just look at, this is just a sanity plot, looking at real spectra that you get, spectroscopic redshift that you get from spectroscopic survey within the same area and compare to your photometric redshift. And then you get a sigma in this area up to redshift 1.5, for example, here, up to 0.05, a very low outlier rate. 7% of the objects are not within 1 or 2 sigma of this line. And the bias is just telling you that we have a real one-to-one correspondence. The same way here, when you get the fitting for the photometric redshift, you get also, by fitting the amplitude, the stellar mass of your object. You can also get, because you run different sort of templates, you can also get, for instance, the star formation rate for these galaxies. So this is this was just an example. This is exactly what you get for the UDS, and because we have 11 bands and very deep bands, you get an exquisite result on the photometric redshift. The sigma is 2%, 2.5%, which is one of the best photometric redshift I've ever seen. We have an outlier rate that is below 2%, and here there's 1,300 galaxies for which we have the spectroscopy at this redshift. And you see that we can probe very good up to redshift 4. So we're using a code called Le Phare that was written by my office mate when I was in Marseille, Hilbert, and Jean Coupon, who's now in Geneva, was a postdoc in Taiwan. We worked together there. Used a method called adaptive templates method. So if you're interested, we can discuss about that. So we get from that stellar masses, star formation rate, age, extinction, etc., etc. So then we want to study the completeness of a sample. So we plot, for instance, here the stellar mass as a function of the redshift, and we looked where we have 95% completeness, which is shown by this red line. So everything that is above is complete. So, and we can do that, the same thing for the absolute near UV magnitudes that we use as a proxy of star formation rate. So now we know how we can divide and split our sample to study it. So now how do we get the gas mass? We get the stellar mass and the star formation rate. So there is one of the fundamental relationships that has been studied now for a very long time, mainly pushed by UKIRT. So it's called the UKIRT-Schmidt law or Schmidt-Limited law. And that is relating the density of gas mass versus the density of star formation rate. And these results are coming mainly from semi-millimeters observations, where you can get an estimation of the gas mass. And it has been surprising to see how tight the relation between those two quantities is. And this has been demonstrated up to high redshift. So as long as you're interested in things that are rather quite star-forming, you have a very, very tight correlation. Things start to break down when you look at galaxies that are barely star-forming. but this is not our goal here. We're looking at star-forming galaxies. So we have this relation between the star formation rate density and the gas mass density. The other thing that you need here is, because we're looking at densities, so you need to know how extended your objects are in the sky to measure the density. So you need a relationship between the mass and the size. So there are several papers that have demonstrated that this relationship for not too massive galaxies, because they are an exception, is following a Poisson law, and this relationship is independent of the redshift. So those two things, basically those numbers here are redshift independent. This is the assumption we're making, but it's really in line with what people are saying in the literature about this. So now we can get a very, very nice relationship between the fraction of gas, or the ratio between the mass of gas and the stellar mass, with the specific star formation rate, which is basically the star formation rate divided by the stellar mass, and the stellar mass of your galaxy. This is the way we're using to probe the mass of the gas. We relate to the specific star formation rate and the stellar mass. But to establish what are those values here, we need to do a very precise size measurements. We need to basically have a real view on the size measurements of our galaxy, which is not the case for the UKIRT UDS. We're talking about very, very faint objects taken from the ground. We really don't have much information of their size. So we use a candle sample that is within our survey, which is HSC data. It's a large survey conducted led by Sandy Faber, so we use HSC data to calibrate this relationship here. So our assumption is not evolving with redshift. So here you have the F gas as a function of a specific star formation rate for different masses in different redshift beams. And once again, we assume no revolution in redshift beams. So by playing this game, we can minimize basically the distribution of those different points, and then we came down with a constraint of those three different parameters, kappa, alpha, and x. So we calibrate that from the candles, and we propagate this information for the full sample, assuming that this lateral area is represented.
So are there error bars at those coefficients? What I mean, basically.
Well, yeah, basically because we're doing a bootstrap. I didn't put it, but we can bootstrap it, and so we have 30,000 galaxies, so we can get down to each pinpoint to several thousands of them. So we can bootstrap. So that's what we're bootstrapping to extract here. Didn't put it there. Yes. Right. So now we have that. So we can basically probe the evolution of what we call intra-galactic baryonic mass function. That means the total amount of baryons, mass baryonic, inside the galaxy. So this is a simple mass function. Here this is the amount of galaxies per element of billion of mass per volume, per element of volume. And this has been done at redshift 0 using radio measurements. This is for Petabytes 2012. I showed you already results from this paper earlier. And then we can't probe redshift 0 because we have too small volume. So this is how it's happening for us when we go increasing redshifts. So here red represents the total baryonic mass. That means stellar mass plus gas mass, and blue is just the stellar mass. The completeness in stellar mass is shown by this turnover here in the blue, and the red line shows you the 80% completeness for the gaseous mass. And the line on the line is not actually a feed from our data, it's coming from another result from another survey, Cosmos survey. It's the stellar mass function from the Cosmos survey. And so we can probe the evolution with redshift up to redshift 4. And as you can see, at redshift 4, we have barely we have no constraint at all. If we want to be very, very conservative, we have no constraint at all on the gaseous mass. With our completeness is good enough. But so redshift 2.
Sebastien?
Yes?
So should I interpret this as saying that your results are perfectly consistent with what's coming out of Cosmos? Because that blue line seems to be... Yeah, so actually, it's not the latest points we have been working very hard to see why we were not in agreement for the high mass end, okay. And we sorted out, actually. We had some problems. Oh, so the error bars are much smaller than the actual points.
Yeah, you can see. The error bars are very small. Yeah. But there are some systematics in our measuring stellar mass. We have solved that problem. Sorry, I should have updated the plots. Why I'm showing you that is because we came up with a way. It's not ideal, of course. The ideal way would be to have SKA ready and giving us data yet. But before we get that, we have a way to somehow probe the total amount of variance in galaxies using these tricks. It relies on the UKIRT law, which is actually quite well established. So basically, up to redshift 2, we can really probe at least the bright end of the baryonic mass function. So just let me focus on here. This is our sweet spot. This is where we have the bin in which we have the most galaxies. And I can show you 3 different things. There are obviously 2 components in the stellar mass function. The bright end. So once again, don't look at the line. We understood what's happening here now. But the bright end and the faint end. And the way people have been interpreting it is actually going back to my original question. At the bright end here, we're dominated by galaxies that are central in the Dark Matter halo. But when you go to the faint end, those galaxies are satellite, mainly, dominated by galaxies that are satellite in big massive halos. So basically, the histories are very different. And you can see it directly from the baryonic mass function. And interesting enough, if you see that where the difference between the blue and the red points, the higher, is more or less at the intersection of those 2 lines. And it's not a surprise. It's because in the low mass end of the central galaxies, you're dominated completely by the gas, which comes back to what I was showing from the simulations. So this is not a revolutionary result. It's just demonstrating that the technique A is working, and secondly, the results we get are making complete sense. So that's a paper that I'm finishing, wrapping up, and I hope to put it out in the next couple of weeks, actually. And well, this is very, very preliminary, but we are starting working on a follow-up paper that is using these baryonic masses and measuring by HOD models the mass of the halos as a function of the baryonic mass, which is what I intend to do from the start. So this is the first result in this redshift bin, the correction function. So you see once again we have the two functions that are high at large scale and small scales, and we can draw the. So this is our halo occupation model, number of galaxies, this is the number of central galaxies, and this is the number of satellites, and they're both following those complex functions, and we have a set of plenty of parameters for basically the correlation here, looking at it. So this is extremely preliminary, but the goal here is from that HOD models, we can extract the mass of the diurnal halos and relate it to a given bin of baryonic mass, and then probe the evolution of the baryonic to dark matter halo mass as a function of halos. And these are to quite high redshift. Okay, so I'm running out of time, but I'm going very quickly to the second results. Just to put you back in the background, so I've talked a lot about the galaxy halo connection. So you have seen the schema several times now. This is a merger tree coming from simulation from the Michel Blezo, medium simulation as well. And here I'll show you that because actually in the merger tree, while the galaxy is evolving, in the tree you see that the colors is changing. And one of the things that we are very keen as well is to probe the evolution of colors of galaxies. That tells us basically what's happening inside the galaxy. Where is the gas? Where are the new stars? Where are the old stars? So it relates us directly with the history. And mergers definitely have, even in those simulations, an impact on the evolution of the color. You see that you have merger on 2 halos that are quite red, and they merging together, they get bluer because you're triggering star formation. So the merger has a direct impact on the evolution of galaxies, and something we want to probe directly. And why we're so interested in that is because we have seen now, thanks to the SDSS, this is a very highly cited paper from Guinevere Kaufman, demonstrated that in the local universe we have a complete bimodal distribution of galaxies between typically low mass blue galaxies and typically high mass red galaxies. And here what you have is a D4000 break that basically gives you an idea of how old the population is. So if it's high, the population is old. If it's low, the population is young. And here this is the H delta absorption line. It's doing the opposite. It means when H delta is high, you have a young lots of star formation, and when it's low, you have very little star formation. And this shows as a function of stellar mass. You really see that there is this very strong bimodal function. So this can be really simply seen if you look at the color. So what we get is that we have this red sequence here, typically those galaxies here, and we have a blue cloud that is mainly occupied by star-forming galaxies. And what we have demonstrated, it's a very early result from the UKIRT VDS survey by Michael Swallow using the data I reduced. And they demonstrate as a function of redshift that this bimodality, so this is just showing a cut if you project everything on this axis. So you see very marked bimodality in colors. But when you go to higher redshift, up to redshift around 2, this completely vanishes. So it tells us that there is something happening throughout the evolution of galaxies since redshift 2. So the evolution of this red sequence is still an open concept and involving something that has a lot of popularity nowadays called quenching. But just first, I'll just show you here, this is the luminosity distribution of, no, this is mass function of, as a function of color. It's a work from Kevin Bundy, from redshift 1.5 to redshift 0.4. What you see is at high redshift, when you look at the high mass end, first, red galaxies were already there. So that means that the most massive galaxies in the universe are formed very early, which was a surprise. But secondly, you also have at high redshift a population of massive blue galaxies that you don't see today. So there's definitely a very strong evolution with redshift of this massive population. And the best schema we have today to explain that, so this is a plot extracted from a talk Sandy Faber gave 2 months ago in Shanghai, is that if you look at this color, so this is human SB versus mass, it's more similar to what I showed you before, you have this blue cloud, and this blue cloud, the evolution here is driven mainly by merging between 2 different star-forming galaxies, what we call wave merging. And then they reach a band that we call quenching band, where for some reason, that can be internal or external, the gas is blown away from the galaxy, and the galaxy suddenly becomes red. Because it can't form new stars anymore, there's no gas. And then this trend keeps evolving when those red galaxies merge one to the other. So there's a very, very interesting work to be done on trying to understand the evolution of this merging as a function of color, or of the merging in general. So this is a topic that has been very popular in the literature for the past 15 years, and even my PhD supervisor did a lot of work on that. And if you listen to each individual, they all show you this kind of plots where you have the merging fractions, so that means the number of close pairs you have as a function of the total amount of galaxies. You can transform it, if you can take a given time scale that is dependent on the mass, you can transform it to what we call the merger fraction rate. Okay? And this has a function of redshift, different surveys, and you can model it with a parallel, because we like to do that, as a function of the redshift. And each individual paper working on merging rate will show you this kind of plot with different values and assuming that they have the best answer. But if you do a more complete work and start plotting the merger fraction of the function of redshift for completely different surveys with different selection, then you get results all over the place. So also lots of people in the literature are still claiming that this is really well constrained nowadays. My claim is that it's not at all, and we still don't understand what's happening out there. And so I will take the last 10 minutes to demonstrate you that. First, what you can see is that in the local universe, the merging rate is very low. 1% only of the galaxies are in action of merging, while we expect it to raise up to 30% at redshift 2. So the merging was very, very important at high redshift. But at high redshift, this merging rate is very difficult to measure. First, because blending is a problem. There are many, many reasons why it's very difficult. And if you look at the literature, there is a real controversy about how much this value of m here is. It's varying between 0 and 5 depending on the Earth. So people are claiming that during their lifetime, galaxies experience 4 to 6 major mergers. That means mergers between 2 galaxies of the same mass. And some are claiming that's only 1. And in any case, even if there are higher measurements, it's still not enough to explain exactly the build of stellar mass of galaxies as we see it today. There's still a question. So when you go to higher redshift, you can also look at the evolution of the merger rate with stellar mass. This is a work from Kevin Xu, and it shows cent per fraction in merger rate as a function of stellar mass for different redshift. And basically, it demonstrates that it's flat. So there's no evolution with masses. It tells us a lot about the physics in action here as well. It's quite interesting. But there is a very recent paper from Fatai that looked at the number of pairs that we have in the local group that trigger lots of my interest. Because if you follow his paper, you look at dwarf major mergers are at the order of 30% in the local group. But if you look at what we get from the literature, we're close to 0. So how come we got a very, very high merging rate in dwarfs in the local group, and at redshift around 0, we have none? It could be a problem on understanding of physics, or is it just the local group is outstanding and it's not very representative? It's a very small volume. So that triggered the work I'm describing now, that is led by Ryan Keelan, postdoc and supervising Academy Synoptic 1, for supervising him. So what we used is the UKIRT survey combined with the SDSS and 2MASS, which is the distribution of our Galaxies sample on the sky. This is the completeness, spectroscopic completeness we get from SDSS, 2DF, etc., etc. So we are more or less 90% complete everywhere. This is the redshift distribution of those different samples. So there is 2MASS with the limit at 13.6, the limit at 15.36, UKIRT, and gamma, which is deeper. Gamma is just those 3 rectangles here. And we have been doing a lot of work in trying to assess what are pairs. And we realized that, for instance, the previous measurements by Xu using similar data sets was based only on 2MASS. And 2MASS is not very good in the blending. So we increased the number of pairs by a factor 2 compared to what is found in the literature in the local universe. So the first thing we looked at is the evolution with the K-band luminosity, because we are using UKIRT, which is a very good proxy at this redshift for the mass. And here I want you just to directly look at things that are comparable. Xu et al., which are the dotted line here, and we have to compare with the blue line here. So you see that we basically double the amount of pairs by doing a very good job in the blending. But globally, we see no evolution with mass, so we still don't understand what's happening in the local group. More interesting, we look at the evolution with the redshift. So if you just follow on our results here, from the local group to a redshift of 1.15, you see a very, very steep evolution. So if I was basing my measurement only for that, I will get as n that is something like 5. But if you include things that are coming from higher redshifts, like the work from Xu et al. From Cosmos, then you get a minor evolution in the order of 2. And we had on our hand another sample called the Red Cluster Survey at high redshift that is a bigger volume than the Cosmos. We're interested in looking at it. And if we take this redshift cluster survey, we get another answer, which is far flatter. So basically, first, if you look at the local universe, you have to be very clever how you're doing the deblending. And secondly, you see that all those things are not very well constrained. And the claim here is that we're completely dominated by cosmic variance. The only sample that is not dominated by cosmic variance is the sample we're providing here with UKIRT. Local universe, we're completely dominated. And high redshift, it's crazy. So here, to prove that, what we have done is just looking at the perfraction as a function of mass within our UKIRT survey, but dividing the survey in different areas with the same volume that we get in the local universe. And you see that you can get down to 1%, which is what we measure. So this discrepancy here can be only explained, basically, by the cosmic variance. And we did use as well the red cluster survey to probe cosmic variance at high redshift. So here what we took is that this is the Xu et al. From Cosmos. Cosmos is actually a very small volume. So we took within the RCS the same volume that Cosmos and do the measurements. And we did 20 or 30 different measurements. And here we're showing the 2 extreme one and 2 randomly selected. You see we can come from something that is very flat to something that is very steep. So cosmic variance is a big concern.
So Sebastien, just a quick question. If one looked at simulations and tried to estimate what we want to expect for cosmic variance from simulations, is it consistent with what you're seeing in?
So we have a 2-page discussion about that in the paper. We can get predictions, but the way you measure cosmic variance depends on many, many different parameters that people not always take into account. They are just looking at the volume, but actually you can demonstrate that the number of line of sight you get, for some studies, having independent disconnected fields is getting a better result than a big one. And also you're very dependent of your ratio. Your stability too is very bad for cosmic variance, for instance. So the Y-X ratio is very important for cosmic variance. So there are lots of works that has been done. So actually the geometry of your survey play a role on the amount of cosmic variance. So if you take into account on all of that, we demonstrate once again that the sample we have from the UKIRT survey at redshift 1 is the best because we probe the biggest body. Okay. So, well, that leads me to a few open questions. And just go to there. What we need in the future, we have already very good data sets, but we need to fit in the future is to observe fainter galaxies at low and high redshift over very large volumes. And the thing is, because we want to probe different environments and really beat this cosmic variance, which is already killing us. And really, for the merger rate evolution, I was very surprised by our results. We had a very lengthy discussion with the referee about it, of course. But basically, the conclusion is we can't probe with the surveys of today anything. And I think HSC actually won't be able to really bring an answer to that. We really have to wait for LSST. So I mentioned HSC several times. You're probably familiar with it. It's a survey conducting at a Subaru 8.2 meter telescope in Hawaii. The idea is to conduct, starting this year, it will end up in 2019. Data is reduced by the Princeton team, which is a direct connection with the SST, because they are building the pipeline as well for SST. This is a HyperSuprimeCam, this is Subaru, this is the first light, Andromeda. The first light happened in August 2012. We get guaranteed 300 nights over the 5 next years, so I've been working very hard with our Japanese, Taiwanese, and Princeton collaborators on the proposal a few years back. And we had our first data last semester, and we're expecting to have 15 nights, so we're slowly increasing the number of nights. And the idea is the wedding cakes distribution survey, as we call it. So we have a very wide area and split it in 3 different places, down to R26. The deep layer is 30 square degrees, the one that I'm most interested in, which is the depth of the full LSST, R27. So we are going to, with LSST, to get 1,000 times bigger, right? And the ultra deep is down to R28. And this is a picture. I'm not sure it's following the scheme, favorite scheme from Robert Lupton here. It's a picture, first picture of Andromeda. I think it's a few minute exposures. You get the full galaxy in one shot. So the field of view of HSC is a 1.5 square degree. And one of the things I'm really keen to do is push the exploration of this mass to baryonic mass to a halo mass ratio to redshift 7. We'll be able to do that. And of course, well, LSST, I'm just jokingly saying that we want to push that to the infinity and beyond. Right, I think I'm completely out of time, so I will just say one word about this. I've been very actively working on probing problems, data mining problems, and how querying the database, etc. A couple of papers there have been submitted as part of conference, ADAS conferences. 2 problems I've been looking at is how to merge catalogs that are from different telescopes. I was very interested in merging UKIRT and SDSS, for instance. So, and that for billions of sources at the time. So we explore with, so it's mainly computer science driven. It's really a project that I've been leading by computer science collaborators of mine in Paris, exploiting the HTM schema from Sally et al. But implementing a version that's extremely fast and able to run on different architecture, HPC. So if you're interested, we can discuss a bit about that. And the other project that I've been pushing when I was in Taiwan, unfortunately, didn't manage yet to go to the bottom of it, is to use different methods to probe the photometric redshift. So I've showed you one method with the MSCD fitting templates, but we have a very, very wide range of tools coming from the data mining community to probe the redshift of galaxies. And so we are trying to work on that and trying to explore a better way of measuring photometric redshifts. Okay, so these are my conclusions. So I've been working very hard in the past decade on different surveys and combining optical to infrared, and I use the clustering in HOD and lensing eventually to constrain the relationship between galaxies and dark halos. We can also use the Gauge law to relate the stellar mass and star formation rate to the mass of gas. And I use that to look at the evolution of variant mass function up to redshift 2, and roughly up to redshift 4. Major merger rate seems to decrease mildly with redshift. Also, it's very difficult to say because we don't really have any strong measurements from the high redshift, mainly because we are completely dominated by cosmic variance. Well, I think it's quite well established that at least in the local universe, major rate is completely independent of the stellar mass. Still not understood why the local group is very different. So there are exciting times ahead. New large surveys are coming. I hope that I will play a large contribution to those, especially HST and LSST. And yeah, there's lots of work to do. Data reduction, as you all know here, is quite tricky, so we want to work hard on it. And I would like to thank you for your attention.
Thank you, Sebastien. Let me open it up for questions.
So one of your last points actually kind of intrigued me, and that was about the photometric redshifts. I was very impressed with the spectacular accuracy you actually got with the UKIRT sample. I would have guessed that at least part of the reason for that it's so good is you have a lot of bands going through into the infrared, right? And of course, with LSST, you don't have that same coverage in the IR. And can you say a little bit about the complications that presents and the ways you might?
Well, there are two reasons why this thing is very good. Is that we're using an iterative method that is using the fact we have very good spectroscopy as well. So the spectroscopy is used as a training set, right. And this is what I was talking about. I mentioned very briefly. This adaptive templates method. So it's actually this the first implementation of this has been done by Olivier Hilbert in 2006, where he was using for the CFHTLS the VMOS VLT tip survey to basically train your template. So because you have galaxies for which you know the redshift, basically you can adapt your template for it to reproduce better those redshifts. So we change slightly the templates that they reproduce better what we get as a redshift for the spectroscopic. And this is basically, you can see it as a way to get rid of all the systematics you have in your photometry that you didn't really realize. So it's not ideal, I agree. I'm always very angry with them because they're telling me that the photometry you are producing isn't good enough. But basically, it's very good in producing very, very accurate photometry. This is one of the way. But I think the first mistake we're doing here, and I'm not the only one, and I'm completely aware of, is we're using photometric redshift as one number, which is definitely a mistake. What we want to use is probability distribution. So we compute them. Actually, I'm using them when I'm doing my clustering analysis. I'm weighing the contribution in the clustering analysis as a function of the PTZ. So I take into account when I measure. One way to do this clustering analysis is you split your sample in redshift and you measure study the distribution within this redshift bit. Or you do it for the whole galaxies, but you weigh your redshift as a function of the PTZ. That's the second solution we're doing nowadays. But this is really in development, and we really need to push for that. So you can see it from this plot here. I don't know what it is. So anyway, we can probe using SED fitting. We can probe the probability distribution. And also, SED fitting may not be the most efficient way of measuring photometric redshift. We are losing lots of information here on the size of the object, on the distribution on the sky. So there are now work led by Chris Benner from JHU, for instance, where using clustering, so the distribution of the sky. The reasoning is because two galaxies that are physically close in the sky are very likely to be really physically close. So their redshift is very likely to be the same. So based on that, they can infer photometric redshift very accurately. And there's a group, for example, Robert Brunner in Illinois is working a lot on that as well. So basically combining all those information together. So this is more or less the scheme of the photometric to the APZ. We are trying to find a Bayesian approach and combine information from different ways of measuring it. But this is as a start. Ideally, what you want is you want a LCD fitting, clustering analysis, unsupervised and supervised machine learning.
Do you use size at all as a piece of information in your PhD determination?
We could. So people have tried. But my initial idea of APZ is that we got a training sample. We know everything of it, and we plot in the multi-dimension. So everything you want to throw it at. You plot it, and you use machine learning things to see how close your object is from those different populations with this multi-dimension. So we start working on that. Very difficult to implement. The other approach would be to use independently different way of measuring this and combine them at the end. So that's the approach made currently by Robert Brown, for instance.
I think we may have time for one more question, either here or someone on Hangouts. So let me ask one last point. So you've shown that you're getting much better at characterizing where the variants are in nearby galaxies and at different redshifts, but fundamental problem of where they're hiding compared to what you expect from things like WMAP still seems to be there. Is that a correct assessment, or do you think that'll get solved?
Just again, what?
I'm going back to the start of your talk when you were showing the expected number of variance and then the actual measured amount of variance. That seems that still is a bit of a conundrum, isn't it?
Yeah, so we still don't know where are all the variants, but the answer is they may not also be inside halos. So there is a big debate, for instance, in the cluster community is what is the fraction of baryons that are stuck in their cluster light. Because if you take galaxies into the cluster, there are lots of interaction, even though they're not merging because they're going too fast. But they can strip lots of stars. And the assessment of that is very difficult to do observationally because you go to very low surface brightness. But it varies from a few percent to 30 to 50% of the amount of stars you have in fact in the cluster. So we're still really at the start. And I would put some note, as I'm not a theorist, but I'm not sure that I don't see any reason why this thing would be flat with the distribution of halo masses. Maybe also you will have a bell shape. You could have a sweet spot for which the basically a given size is preferred for halos than others, and this probably will evolve with redshift. So I put a flat distribution, but it's probably not. You may have preferred scales in fact in distribution of that matter.
All right, well, let's thank Sebastien once more. And thank
you.
And Sebastien is going to be here for the rest of the day, and I think tomorrow he's also in Tucson. But
he'll probably be in the area
that he's going to be at. But if you want to talk to him, now's your chance to either talk to him now or schedule a meeting for later today or tomorrow. Thanks.
Thank you.
So,